Welcome back to another episode of Network Forensic Fundamentals. My name is Phil Hagen, and today we're going to be talking to you about the PCAP file format. And this is a concept that's really important for us as network forensicators because this is the container for a lot of our evidence. And even though we're not usually all the way down into the byte level review of the content of these files, it's important for us to understand how our evidence is contained because a lot of times it's going to be directly driving what our tools are actually telling us. That's the really important thing for us to remember here. Now, the PCAP file format is very well established. There's a couple of different versions that we're going to be talking about. And it comes through what is a library that is commonly used in a lot of applications, which is called libpcap. And it's going to provide this format that we're going to talk about, as well as some of the other filtering capabilities that we'll discuss in a future episode. I'm going to talk to you a lot today about what the legacy PCAP file format is. And I'll get into what the newer version is in just a moment here. But the legacy file format is one that's been around for a very long time. It's very well established, and it's quite universally supported with a lot of our network-focused tools. I'm going to talk to you today about what the format is, what the structure is of this file. And again, I never really expect that you as a forensicator are going to be looking at these files in, let's say, a hex editor. But it is important for us to understand these fields, and we'll talk about what some of those fields are going to report back to us through our tooling. Now, at the very beginning of a legacy PCAP file is what's called magic value. And these magic bytes will always be the hex values D4, C3, A2, B1. This is going to tell Unix-based or Linux-based utilities that this is a PCAP file format, that's what it's contained in here. The concept of a file name, specifically an extension, is cosmetic in the Linux-based world. Therefore, we need to look at the actual content itself. And that's where that first four byte value comes from. Now, the next two values are going to be a version number. And this is going to refer to the PCAP file format specification of what you're looking at in this particular file. Now, long ago, this was a lot more relevant. Nowadays, you're going to see everything is going to be version 2.4 because that spec has been around since libpcap version 1.1.1, as you can see. But this is just something that is already established as a part of the file format. Therefore, we need to maintain integrity and maintain consistency with that file format. So these days, all of your legacy PCAP files are going to be 2.4. Then we have two reserved bytes. These are actually kind of interesting as well. Now, in practice, in any modern day PCAP file, these are going to be zeroed out. You're not going to see any values here. Now, in the original spec and the original intent here, these were reserved for a time zone offset as well as an accuracy value. So it would tell us how far away from the UTC time zone or Universal Coordinated Time, all that the timestamps are in the file. And it would tell us if you have any more than 6 positions after the decimal point in your timestamps. In practice, all of our timestamps were converted to UTC, which is certainly a great practice, one we should all try to follow. And in the time accuracy, the timestamp accuracy, they were all down to microseconds, which is those 6 digits after the decimal point. That said, we can't just skip over these because we no longer need them. So they're zeroed out, they're considered reserved. Those generally aren't going to be used. The next value we have is what is called the snapshot length. And the snapshot length is a value that refers to the maximum number of bytes that the utility that created this PCAP file was told it's allowed to take. Now, at first you might think, wait a minute, if I'm doing packet capture, why don't I want all the bytes? In a lot of cases, that's correct. But what if you're in a situation where you're legally prohibited from capturing content and you're limited just to headers? You might want to limit the number of bytes you have, and then you never have a possibility of capturing more than you're allowed. Or maybe you're looking at a shortage of storage space, and instead of all of the packet content, you're going to go ahead and say, you know what, just give me the first 100 or 200 bytes. That might be a decision that you would make to trade off space for completeness. If that is specified, we're going to know how many bytes were requested because that snapshot length is going to document it for us. Now, if you have what we would call an opportunistic packet capture, meaning it's a packet capture that contains all of the available bytes, then this is going to indicate a very high value. It's going to basically indicate 64 kilobytes worth, which is far larger than any frame of network traffic would be. And then the last 4 bytes that we have here are going to be the link layer type. There's quite a large variety of these. They are specified by the original documentation for the PCAP file format. You might see that one PCAP file contains Ethernet, another might contain 802.11 traffic. You might see other types of framing protocols in data centers or on internet backbones, for example. That encapsulation at layer 2 is what we're talking about. It's going to be what is the actual content at layer 2 for the packet that immediately follows. Now, before we go beyond this packet header, the file header, let's talk about the fact that this 24-byte value, this 24-byte sequence must be present regardless of whether there's any packets in the PCAP file. So if you have an empty PCAP file with 0 packets in it, it's still going to be 24 bytes in size. It's going to be these values right here, because these 24 bytes will occur at the very beginning of each and every PCAP file. Remember, that's going to be the legacy PCAP file, but that's still what we're talking here. Now that we've got the header portion done, let's talk about what the packets look like. The packets themselves actually have a header as well. Now this header is much simpler. Each of our packets that's contained in this PCAP file contains 2 time values and 2 length values. As you can see here, the time values indicate the number of seconds and microseconds for when that packet was observed. These are in Unix epoch, or maybe you say Unix epoch file of timestamp format, which indicates the number of seconds, and in this case microseconds, since January 1st, 1970 at midnight UTC. Very commonly throughout all Linux and legacy Unix-like operating systems, this is the timestamp that is used to represent the current time or any other time value. It's usually going to be just the number of seconds, but we've added on those microseconds as well. Now, an important point here is that I'm specifically talking about the time the packet was observed. It's not necessarily the time it was sent or the time it was received. Because if you are observing this network traffic somewhere between the sender and the receiver, you might think client and server, for example, you're going to have some period of time that elapses between when it was actually sent and when you observed it, and then some other period of time that elapses between the observation time and when it is received. The only timestamp that is known is the timestamp on the clock of the system doing the observation. So that's the timestamp that we actually get. All right, now in practice, the amount of time between sender and receiver is usually going to be quite small. It's not a guarantee, it's measurable. It might be tenths of a second, but I like to be very precise in my phrasing. So I'll always say observation time if that is a clock value or a time value that came from a system that didn't have true knowledge of the sending or the receiving time. Then we have our 2 length values. These are pretty straightforward as well. This is going to be how many bytes were captured. So this will be how many bytes are actually in this PCAP file for the following packet. And then we have a value that indicates how long that packet was, how large the packet was before it was truncated, if it was truncated. And that actually goes back to our snapshot length. Let's say we had a snapshot length that was specified that says, I'm only going to keep 54 bytes of traffic. And that's generally going to be enough for an Ethernet header, an IPv4 header, and a TCP or UDP header. That's a TCP header with no options included, of course. Those 54 bytes might be all I'm allowed to capture. So my snapshot length for my capture utility would say only keep 54 bytes. Now, if the original packet that follows this particular header was, let's say, 1500 bytes, it's a pretty common value of a maximum transmittable unit or an MTU on a given Ethernet segment. If it was originally 1500 bytes, but we only kept 54, then the length of the captured packet will say 54 bytes, and the length of the untruncated packet will still tell us that it was 1500 bytes. So at least you and I are going to know how large that packet was before it got chopped off by that snapshot length. Pretty useful information, and a lot of our tools are going to report this to us as well. And of course, I have been referring to the legacy PCAP file format, and this is still one that I prefer to use. I'll explain to you why. The PcapNG, or PCAP Next Generation file format, was originally proposed way back in the year 2004. That's a long time ago. It's still a draft standard, and as a draft standard, it is still subject to change. And as a draft standard, we tend to see that utilities that use and allow the PcapNG file format don't do that as consistency as we might like. As the consistency needed for your forensic functionality there is very, very critical. I want to make sure my tools are returning useful information, valid information every single time. It's one of the tenets of proper forensic tooling, of course. So the fact that we have some tools that don't fully, completely, or equivalently support PcapNG is one reason that I personally try to stay away from that as much as possible. Now let's talk about why PcapNG is better. What does it provide that the legacy PCAP file format does not? It's actually pretty useful. It allows you to put multiple different capture interfaces or link types inside the same PCAP file. That's great because legacy PCAP, you're only limited to one. We can embed comments even after the fact, which, as long as you have write access to your PcapNG file format, it's a great way to add in information about what's relevant or important or concerning about content of a given packet. And it also has a built-in ability to go to a much more detailed, much more precise timestamp. There's a couple of other valuable features that the PcapNG format adds in, but those are really the big ones that we as forensicators are concerned with. But again, they come with a trade-off. We have these additional features, but our tools may not fully support them or may not consistently report back the contents or the nature of that file. So my recommendation is if you receive PcapNG data as evidence, don't get rid of it. Make sure you keep that. But I like to convert that to legacy PCAP file format so that I know my tools are going to support that in a much more complete manner. That ends up being really critical, of course. And there's a lot of tools that can actually do that conversion for us. The example that you see on screen here, this edit cap command, is actually a built-in or utility that's provided along with the Wireshark toolkit, which we'll talk about in a future module of this channel. And it's a tool that allows you to do a variety of different manipulations of PCAP files, including changing how they're encapsulated, what file format they're using. So you can see here, I have a PcapNG file format indicated by the result of the file command. And then when I run this edit cap command here, I convert it to a new file, not modifying the original, and you can see that this is now a PCAP file format, as indicated by the results of the second file command. All in all, this ends up being an incredibly useful way for us to ensure that our tools are going to consistently and accurately report based on the PCAP contents without ever actually getting rid of the PcapNG original data. This is definitely my preferred workflow anytime I'm working with packet capture data that happens to come in PcapNG file format. A little word of caution though, if you do use this trick, you are going to lose all of those added benefits of the PcapNG file format. That's fairly obvious, but it certainly bears mentioning just because we have to try to make the best trade-off decision that we can. That's just a little bit on the PCAP and PcapNG file formats. Really important fundamental concepts for us in network forensics. Have to do how your evidence is collected, how it's stored, for example. And as we're going to see coming up in future modules, it also is important for us because we need to know what our tools are telling us. A lot of that information will be coming from these PCAP file format. Hope you enjoyed this second section here, and we're looking forward to talking to you a little bit more in future modules.